first. And what I learned there, I could use it somewhere else. So we are all trying now to understand the challenges of our world, understand how we could fundamentally make more by consuming less. So the concept of efficiency, the concept of doing less physical prototypes, spend as much time as possible not using energy, is our new effective challenge and our new drive as engineers and technicians and any scientific member of any technical community. I recently, well, like a couple of years ago, moved in aerospace. So again, come from Italy, 10, 12 years in racing, then went in passenger cars. Now I'm working on electric planes. How does it work? How could somebody do something like that? First, I always did what I liked. And when I like something, I go in head to toe, really go in with my passion. And then I always try to learn on my journey and apply what I learn. So from racing, you understand that some people may believe or may think that racing is, please forgive me, agricultural, so you just need to get it done quickly and dirtily. In reality, you need to be extremely focused on using exactly what you need and only what you need. Don't add anything that is not needed. That is weight, is efficiency, is time to get your design through. And that is what you learn and you can apply everywhere. Moving to automotive, I'm not saying that racing environments are not regulated, so you need to compete there and there is a regulation, but passenger cars are for mainstream, for public. I've been exposed to the regulated environment, so right, doing something exactly as is needed is not enough. We need to get it done and follow some rules so that all the customers are safe. Moving aerospace fundamentally is almost the best of both worlds. So the regulations are a little bit more stringent than in automotive, but the weight is as well more stringent than in automotive. So it's kind of bringing me back to the beginning of my journey. Long story short, if you want to do something and you want to change your direction and you want to explore something, please be brave and do it. Try to discover and explore what the future is giving you. Last but not least, thank you ever so much for being here. It is a pleasure, it's an honor to be here with you today. Let's try to enjoy the Design Challenge Regional 2023.
Yes, thank you. And let me invite Volga to have a welcome address.
Thank you, Pinfei. So welcome everyone to this challenge hosted at Kingston University. I'm Olga Duran, I'm the head of the Department of Mechanical Engineering. The department is part of the School of Engineering and the Environment, and we have 4 departments. So 2 of them, civil engineering and geography, are based here, while mechanical engineering, aerospace and aircraft engineering departments are at Roehampton Vale. So we have a long tradition of hosting that event. I believe we hosted it in the first year when it ran. My colleague here just told me it was in 2016. I think it was even longer back than that. I start counting, but I ran out of fingers, so I cannot remember when it was, but we hosted, I think it was the first event at our other campus. And this time we have the opportunity to host it in this award-winning placement at this other campus. But I invite you all, if you have the opportunity, to come to our other campus where we have all our engineering facilities. Just something funny enough that when the judge gave his speech, he came here to this country in 1999 in July. I also came to this country in the same time, so maybe we met at the airport. I don't remember his face, but we came at the same time. He's from Italy and from Spain, but also I've been here for this amount of years. Again, I've run out of fingers, so I cannot count how many. So I don't want to make it that longer, because I'm sure we want all to see your devices and everything that students have been building, and especially seeing them running through the test rig. But I would like to thank the technical team at Kingston University for building and bringing here from our other campus this rig that looks great. I hope everyone agrees. Also for IT for filming, Pinfei for organizing, everyone else who has been involved, as well as the administrators who have taken care of everything behind the scenes. So thanks very much, and of course thanks very much to all the students who have taken part, because I know you've been spending endless hours above of what probably was in your it was expected from you to build. Look at the devices, they all look great, and I'm sure we will have a lot of fun seeing them, hopefully reaching the top and coming back, hopefully. And I hope you will retrieve them and they will not get destroyed, because this fluoride tech is quite hard. Unfortunately, now our other campus is carpet, but here, hopefully, will be controlled. So thanks very much to everyone, and enjoy the day.
Thank you, Olga. And now I have some just very brief. So I know, unfortunately, this is blocking the view a bit, so I'm just going to bring that up. So first of all, can I announce the 3 teams that got selected for do the live presentation later on? That is Kingston University Team A, Hertfordshire Team 1, and UCL Team A. Okay, so please get prepared for do the live presentation later on. Okay? Yeah, you did a really good job on that. And then just some health and safety announcements. You can see the fire exit is on your left. So if there's an event of an alarm and fire, please access through that door. And if you do need any emergent care, speak to the reception where you entered, over there behind this door, and feel free to grab coffees, pastries during the event. Yeah, and yeah, we're just launching SolidWorks. Sorry about that. Just a quick run through the outline of the day. So the next part will be doing design review by our head judge. So whoever is called, please come here and ready to be asked. Yeah. And after so the first year will be reviewed first, then followed by the second year. And after that, we'll have the presentation competition. Okay? Thank you. That's great. Thank you. Just plug it in.
Can we please have, for the first year, Imperial College London A? Can you please come? So I'm loading your CAD.
I don't know whether you can do it like that, or you have to sometimes open it through SolidWorks. Oh yeah, it is open.
There we go. There we are. So, can I see the device? Right. So one of the aspects of the design was to, double check or compare the real life thing with your CAD. What I see there is that you put. I'm just trying to rotate and then do a cross section. So you put most of the feature that are there, but then what you produced is not exactly what is in the CAD. Is there a reason?
Yes.
So there are a lot of differences between the, well, some differences, the concept is there, but there are some differences between what we see in the CAD and what instead you're showing here to us.
The main difference is that we added an extra stage of reduction because there's not enough torque.
Okay, so you did that one without going through the CAD design activity, so you just went on the prototype and modified that one there.
Yeah.
Am I right?
We added it after we submitted the file.
Okay, that's fine. Where is the battery located in this device?
Should be here.
Okay, so it became detached. I can't see the battery on this component here.
Yeah, so the back section is reserved for the battery.
Okay. When I checked the CAD, I couldn't find any fixing, and I realized now that you didn't have any screws, so it's all either glued or press fit.
Just fit it. We don't need any glue.
So you just fit that. Okay, that's why there were no fitting over there. Could you please tell me what have you found a little bit challenging, or what you have found difficult in modeling this component, this design?
I mean modeling or the actual?
Yeah, we're talking about the CAD modeling. So what was your main difficulty between getting it to look like the real thing?
I think the main problem is the tolerance of the 3D printing.
Uh-huh.
Because it is additive manufacturing, so a lot of holes smaller, and yes, I think that's the main difficulty.
Did you think that by doing the CAD exercise you learn something about working with the tolerances, or understanding next time how you could possibly get it a little bit better?
Yeah, I think I did. But now I have in mind what holes should I make to fit a 2mm shaft.
Okay, that is one of the examples where the design and practice could go in a different order. So you could have done a mock of different size, print it, and then check which one from the CAD was giving you the right result.
But basically, every printer is different, so the model doesn't really.
Okay, so your printers are possibly.
Yeah, we are using public printers.
Oh, you're using public printers. Okay, fine.
So it's everyone different.
I couldn't really understand how you were gripping, and I see now that you have put on. What is this?
Neoprene. The rubber is neoprene.
Is that the rubber for like a tennis racket or anything like that?
Door seal.
Door seal.
Kind of.
Okay. And does it work?
It produces enough gripping force. It keeps the stuff in the tube.
Uh-huh.
Falling.
And where is the attachment for the chain? Right. So you hook over there, and is it okay? Is enough that grip to get the chain up and come down? Yeah. I mean the grip is enough to with the weight of the chain.
Yeah, the main problem is not with the friction, is with the gripping force, the pressure. Sometimes the pressure is too big that it doesn't even move.
Okay, I understand that one. Understand. Oh,
Sorry,
I'm not
hearing me.
I'm not really used to use microphone, so that would be great. So they mentioned that nobody could hear you apart from me, because I was not handing over to you the microphone. So could you please repeat for your colleagues what was the issue with the grip?
The friction force from the rubber from the PVC tube is enough, but sometimes it will climb sideways and deviates from the center, so the pressure will be too big and it will not climb. Sometimes it will get stuck.
Understood. So that was one of my questions. So with effectively a single plane kind of design, how you ensure that it stays in the mid plane? So sometimes it doesn't.
Sometimes it doesn't.
Good. Right. I think that I'm okay. Thank you very much for your time.
Thank you.
Thank you.
Yes, please. So the number 9 this is something that we need to guess a little bit. Number accuracy of the, I think is not very accurate. And then the last one that we have, number 10, design review. Let's be generous. Imperial College B, please. Fantastic. All right. Okay, let's get. So I've been told that the physical. Oh, is your team. Okay, good, fantastic. Thank you.
So.
Could you please describe the robot to everybody, how you did, what you did, and what you found out? Okay. I understood from your presentation that you declared that you didn't cheat, so.
We did. Thank you. Yeah, so basically our design, we have two driven wheels. So these are here. We have a drivetrain that goes from the motor in the middle all the way to the top, so it splits here. And at the splitting, we have a drive shaft in the middle, which we knock out using this rocker. So that kicks this gear out, and then it just free falls down the pipe if it reaches the top.
Correct.
Yeah.
With crash protection at the bottom there.
Yeah.
Thank you.
Yep.
What else?
What else?
To constrain it in the pipe, the wheels hold its center line, and because of the curvature of the pipe, it keeps roughly center. And then we've added these supports either side, which keep it and stop it from twisting too much in the pipe. Because I'm sure, as a lot of you found out, when it twists, it then gets jammed and leads to all sorts of problems. The battery connection, we've just wired that into the switch, which hangs out the bottom, so the device handler can switch it on and off easily without getting too caught up in the pipe itself. And the batteries are secured in place underneath with the bubble wrap, but the idea is that they can be changed out quickly should they need to be, as they do drain quickly. Oh yeah, chain attachment. Do chain attachment?
Yeah, so the chain's attached very simply. It's just a piece of string with a knot at the bottom, and you just loop it over and then tighten it. Yeah. It's pretty straightforward.
Lightweight.
Lightweight, yeah, does the job.
Yeah. All right.
Couple of questions from my side. So we are here to double check the CAD accuracy and how the CAD relates to the model, which is always a little bit of a challenge. I see that you took a few shortcuts. One, that was one of my questions, but I now see the chain attachment. You remember that from the regulation you have 1 minute to connect the chain and prepare, change the battery and everything.
Absolutely.
So if between two heats you need to replace the battery and attach the chain, do you have time?
Yeah, we've tested it. We can
Good.
do it in time. The chain attachment only takes 10 seconds. You just push that through and it comes off.
Okay, good. Other things, I was puzzled about the absence of fasteners, but now I understood that you, as the other team, are not using any fasteners, so it's either glue or just press fit. On these wheels and gears, it seems a little bit not really control the lateral movement of the gears. So how did you manage to get the gears always to be in line?
Yeah.
We have some spaces which are interference fit on the shaft that hold it there enough, and there isn't actually that much load that goes through it to move them out of line, so we haven't had many issues with that. Any bits that we have had, we have made sure that the gears are always in contact. We've added extra gears to ensure that, and we've kind of used this to our advantage with our rocker mechanism to remove the shaft from the drivetrain itself.
Okay, so my understanding of your device is that you will go for the kind of free-fall descent.
Yes.
Have fun.
Thank you.
Good luck with that.
We've tried. It's a little bit sketchy at times, but it falls down the pipe. Because it's quite a tight fit on the inside, it doesn't free fall all the way. It'll free fall and catch at points. So, but it does land quite hard. But the bubble wrap's been fine so far, so we're hopeful.
Good. What is the biggest difficulties that you have found in using the CAD and then translate it into the reality?
I think Yeah, I think it's updating the CAD every single time you change a little bit, a small detail on the model. So let's say you change the chassis, and then that will change all alignments of, let's say, the mates on the CAD, and then you might add bits, and then add these. For example, for us, we added these guideways, but we didn't have time to add on the CAD. So yeah, that was the main challenge.
Yeah. And with the submission date being 2 weeks ago for the CAD model itself, the majority of when we were doing the testing and we get closer and closer to the event to try and ensure that it works smoothly, we did quite a lot of modifications after the submission date had taken place. But we focused on getting a product that worked, having given it our best shot in our initial submission.
Understood. Thank you.
Thank you.
Can we please have a Kingston University? I think there is only Team A. Or Kingston was the one that they were late.
I think so.
You are the one that were late. Yeah. Sorry. Fine. Yeah. Sorry, I will move on in the next one.
Sorry to interrupt. So for the presentation, can the three teams have you got a USB stick? So could you, because we don't have the presentation, so it would be really good if you can provide us with the presentation. Have you got a USB stick that you can just plug into the laptop? If no, you have, okay. If no, just come to me, meet me here, we'll sort it out, okay? Yeah, all right.
Can we please get Hertfordshire 1? Do you have your product with you? Thank you. No, it's loaded. I just got this laptop now, so I'm trying to. Really? There we go. Good, you are the Leafspring team. Yeah. So just let me please hide a few things that SolidWorks kindly always put together. Right, the accuracy between your model and the CAD is quite good. Could you please flick it together? So you have a different battery pack. Yeah. doesn't seem to see the electronics that you have used or the electrical board connection that you have used. But apart from that one, is relatively accurate. You spend your time in finding the nuts and the bits and the bobs, so good one. Tell us about, what is your thought and your design process in transforming the CAD into the reality, or the idea into CAD and then into reality. So what have you done?
Well, firstly, it all started at a piece of pen and paper, and we tried to go with something very simplistic, and it was very inspired by a leaf spring from a pickup truck, and we decided to go with the leaf springs, and it was also inspired by what way the handle on a flash bottle for the flash spray. So they use springs which are made of PLA plastic, and we try to use this idea in combination with the slots to make leaf springs, which compress onto when the model is placed inside the pipe.
Okay, understood. How are you attaching the chain to the end?
The chain is attached through the screw on the back side. So we unscrew it, place the chain through, and we screw it back together on the springs.
So you're repurposing one chassis component to be as well the attachment.
Yes.
Oh, quite interesting. You did a good design. You did spend a lot of time in the leaf springs. Clearly, you didn't have time to model the wiring around it, and is the messy bit of the part.
Yes.
What did you learn from this journey?
Well, I learned that we have to start very early, and to think about these other complex bits. But overall, I think I know many areas which I could improve, like in terms of weight and wiring, mostly.
And what consideration did you give to the weight in the design? As you say, there's opportunities to reduce the weight. What was your thinking early on?
Like in future, if I were to do it again, I would have made many holes throughout the chassis just to reduce the weight.
And why didn't you do that? Yeah, why?
Just because of time. That's the honest truth.
Drilling holes doesn't take time.
You know, there's some I had to do some fidgety bits on the end, which I had to do a lot of soldering, and there were some delays to it. But that was just
understood. I read on your poster around the tuning of the leaf springs to get the right stiffness. Could you talk through the design process and perhaps practical iterations that you made? Somebody else?
So while we made the leaf springs, we experimented a lot on the stiffness. And even when we firstly made the design on CATIA, then transferred the design to the flash print, we played with the density and infill percentage of the leaf springs. So we have experimented a lot. We brought all of our leaf springs that we wanted to use, but we didn't. And the last version, this one, was perfectly stiff, I might say. And then while we made our calculation using the MATLAB, it was like the exact same number that we took for the creation of the leaf springs. So the radius of the curvature was like 55 millimeters, and this is 54.98, I think.
So you experienced manufacturing tolerances here. So,
especially printing. Yeah.
I really like to see your. It's still live. I really like to see your CAD and the time that you spent in detailing all the bits and bobs and the little components. As you can see, there is a difference between your 3D model and your real thing. So the battery holder is slightly different. The switch, the inverting switch on the top, is again another device. There was no evidence from that one that you were doing a little bit of analog circuitry in there. So my suggestion to you is that you did a great job, as you suggested. Taking holes out from 2 bits of laser cut chassis, I think it was achievable.
Yeah.
So whenever we reach a level, always try to challenge you to the next level up. Otherwise, you will not stop. And detail as much as possible in CAD will help you to understand which issues, or at least write down which are the risks in your development.
I think the key thing about this whole challenge is it is a competition, and weight is clearly going to be a differentiator along with the traction, etc. So you know, I think to me it's right up there in how do I make it as light as possible, and which is why I pushed on that particular topic. I don't think it's an afterthought. It should be kind of at your forefront. How am I going to make this as competitive as possible, as well as achieving the task of going up and down? But good. Any further questions? No? No, thank you very much. Thank you.
Thank you very much. Can we please have a her for share 2? Together.
Oh no, it was completely different.
Yeah, I know, your device is the one with the spring in the middle.
But this one, the circuit was the same, but the concept was different, and then slowly it came back.
Fantastic, thank you very much. Are you the only one rep today?
Yeah, unfortunately.
That's great. I don't want to make you feel that we are giving you our time because we are asking everything to you. So, your design together with somebody else had a very high level of accuracy on the CAD. So there were good position of the switches and all the other stuff. I see that you have not modeled a lot of stuff like the wiring, the circuitry, the fixings, the nuts, and everything.
That was done after the upload, because most of the iterations were done our iterations were done in the last week. So we didn't upload the final model, so to say.
So how did you manage to do the CAD, do the iteration, and do the other stuff? So what was your design and review process?
So our design and review process was make it and then see if it goes up the pipe. The first 2 iterations, it didn't go up the pipe at all, and I found out that it was an alignment issue. So what I did is I added a centering sort of thing. I don't know what you'd call it, but to center the spring so that it wouldn't make a torque on the overall frame, because that was the main thing that was stopping it from going up and down the pipe, because it introduced too much friction.
Okay, understood, and that is a good learning that you can put together, and I'm sure that next time I will design from scratch, thinking about the position and the movement of springs whenever you need to deal with springs. As you can imagine, we are here to kind of, one of the scoring criteria is check what you brought to the competition and check what you submitted in CAD and see how different or accurate or non-accurate they are.
Also, one of the main thing was that the weight reduction was not possible because of the laser cutter was broken, and it was quite last minute, so it was just, yeah.
Preempted your question.
Yeah, yeah, fair enough.
Do you want to?
Okay. I mean, just going back to the CAD, you know, the idea of using the CAD system is to formalize the design ahead of the manufacture. It feels like we've done it slightly around the other way, but yeah, as David said, lots of learning to take it forward. In terms of the drive mechanism, what are you using? What was the drive?
There's a motor connected to a coupling which connects to the wheel, and we had to use a coupling because the shaft was different for the internal of the wheel and the external of the drive motor.
And the compression on the tube to ensure tractive force?
We use the spring. We only do one spring because it's a triangle well, so with the one tension made all of them push out. So that's why since the beginning it's been like this, as you can see.
And the reversing mechanism is a simple switch there?
It's a double relay switch.
And it drives back down again?
Yes.
Yep. And in terms of stopping at the bottom so that it doesn't just fall onto the floor, what consideration?
I found out today that we can't actually hold the device.
I think it's clear in the rules.
I guess I didn't see it, but I thought we were allowed to catch it when it dropped, but just today I found out that we were not allowed to. So.
I look forward to the competition later then. 3 runs.
Hopefully.
Good.
Thank you very much. Can we please have a UCLA? Thinking about loading the card, don't worry. It may do something.
Is it this slow at home? Yeah.
Yes, automatically translating the step into an assembly. Is always no, is a SolidWorks thing. So right. Thank you very much for being here. I understand that you printed everything. I understood that you were printing everything black PLA because all your CAD model is black and is. Yeah, the thing is that when you export in a step, it could corrupt. So that is the thing. So I thought that you made everything black, and it was really difficult for me to understand. You have the battery, which is looking like it's hanging off the thing. How is it really designed to be?
So initially we had a 6-volt A544 battery put here, but then during testing, we found out that as soon as you put it in the pipe and there's some resistance, the 6-volt capacity drops straight away to 2 volts. So this was a pretty much last-minute change to 4 AAA batteries. That's the reason why. So, and it's a lot bigger than the initial smaller 6-volt, so we had to leave it dangling as the only option.
Okay, understood now. Now, in your CAD, I couldn't really see how you were controlling. So I thought these were bearing, and in reality, what I see that you have as well some. Bearing. So they're bearing with the press fit. Yeah. Okay, and everything is press fit. There are only a small number of screws. Am I right?
Yeah, there's not really any screws anyway. Everything's press fit.
Okay, so how are you planning to deal with the descent?
So we have a DP/DT switch at the top. Once it reaches the top, the switch closes, reversing the current in the motor. So the wheel reverses direction, driving the device back down. It drives back down.
And on the landing?
Landing, we have polyethylene for that reason. Cushion impact.
And with the hanging battery, so have fun.
Yeah, that's why we put that out there as well.
Good. So what have you found challenging of doing the design and creating the physical part and doing the test? So what you think you missed in the design analysis of the risks to prioritize and focus so that it could make your life a little bit better?
Do you mean like what could we have done to this device?
In general, when you do something, you would like to do analyzing design and scope out any risk or any issue or anything as much as possible before you build something, because building is always low. So you need to buy the material, cut the material, assemble the material, and then test if they work. So normally, what you could do is a balance of how much time I need to spend in the design and how many risks will take me longer to analyze in CAD or in virtual world. And I could say, right, the time is better used on a practical device. So the way I see it is that you changed almost dramatically the battery because you didn't calculate the right power. Could have you done something differently to understand that you needed more power for your run, or that your device was going to have a different weight and therefore deliver a different load when you go up and anything like that?
Yeah, we could have made changes. So like even we had a few short circuits on our device when we tested it. So what we changed was our DP/DT switch. We changed it, so now it works a lot better. We don't have that many short circuits when we run the device now. But yeah, when testing, we found that it works pretty well. So we haven't really seen the change. We haven't really seen the need to change anything for now. But yeah, all the changes we've made were after doing Excel simulations and everything. We tested it practically, and these were the changes we made.
Microphone. And so on the mechanical side, in terms of the tension, I see you've got some springs there to provide the tension. Did you make any adjustment? Was that did that agree with your calculations, or did you have to make adjustments to that spring tension to get the force that you needed?
So upon making the device, with springs that we bought, we kept testing by cutting down different amounts of loops and putting in the pipe and see what works, what doesn't, and then.
So in that sense, it was an iterative process. How do you now have a better understanding of how you can better model that to get the force? Because you now know the spring that you're using. You should be always looking to go back to understand where your calculations could be improved going forwards. Okay.
Yeah, that's also one of the reasons we added a zip tie to help with the tension, because we found that when going up, it does stretch a lot and it could even like break the wires. So that's why we've added a zip tie there to help with the tension.
And I think the other point, general point here, you said that you built it all, put it in the pipe, and then found that the battery was not appropriate. You could also think about some subsystem testing as well. Could you have run the motor with the battery prior to building everything, and already learnt that you would get challenges with the battery that you chosen? So before you'd actually assembled everything and had to then kind of pretty much tear it up to accommodate the new battery. So all good learning steps to take.
From my side, a couple of jokes. One is that a thank you, because you tried to model at your best all the wiring, which some of the students believe is hard work. You did it, so well done. Really appreciated. The other one is that I was a little bit amazed by a wireless fixing here. So I wanted to understand how you do a wireless fixing of a wheel. It's a joke. Thank you very much. Thank you.
I think it's called a low friction bearing. Yeah, yeah, very
low friction.
Very low friction. Good. Thank you, guys. Worryingly, I can't work out how to turn the microphone off. It could be dangerous.
UCLB? Well, whenever we decide is a good time for.
So next one to UCL.
B.
B. UCLB, next please.
While it's loading, I will ask you a couple of questions. So I really, when I was going through the CAD and the presentation, your team was the first one that decided for that I came across that decided for the free fall. So the regulation say, right, this is trying to replicate the pig to clean the pipework, but in reality the challenge is telling you need to go up and come down in the shortest time possible. So from one perspective, I say, right, you didn't really try to simulate an industrial device. From another perspective, so you read the regulation and stick to it. So, well done. It was interesting. How did you find it was the right density and the tension for the bumper? You just did one and it was okay with you?
Yeah, we chose to use 95A TPU because I've experimented with printing TPU, and I thought that would be the hardness that would fit the purpose, and I tried it and it seemed to be good the first time, so we didn't print any other versions of this piece.
And just looking at it as it goes out the pipe, do you find that there's a friction concern as the bottom rubber kind of rattles up the pipe on the ascent?
No, it doesn't, since both our wheels are driven. It goes up pretty evenly in the pipe. And the first thing that would slide along the pipe would be the top frame and not the bumper. The top frame, which we've sanded down to be a smoother edge so that it doesn't slow down the device.
Okay, I see. Could you just talk us through the drive mechanism, your gearings there?
Yeah, it's just powered by 2 batteries. The motor is geared, and yeah, there's a 5-to-1 gear ratio where it powers these 2 motors here. And this DPTT switch, when it hits the top, it will reverse the wheels, so it just drives back down. And obviously we don't have a stopper mechanism, so we have this bumper here.
And we've spoken about the free fall. How do you disengage the gear drive when you get to the top?
Oh, it's this. Do you want to explain?
Yeah, the BT2 switch.
Take the thing. I'll hold it like this. You can turn around. Take the.
Basically, we use a DPDT switch. We
which is placed vertically, initially placed at the top,
And then it
and basically touches the top because of the force going up, and then it pushes the DPDT switch down, and changes the direction of the motor. Initially, the DPDT switch was placed at the top, like here, but we realized it wasn't efficient, it didn't work most of the times. So you place it vertically, so more force on the DPDT switch when you touch the top.
can I just add something on the switch? Actually, at the beginning, it used to be a rocker switch, but we changed this because there wasn't any practical way of attaching a probe to it that it would work every time. It was a bit rough.
That would be my question, because by looking at the CAD, I saw a massive, long, and potentially flimsy stick that was coming off. So you have this thing here, which is very, very disproportionate in terms of diameter versus length. So I was thinking if they go up to a decent speed to get a decent timing, it may bend. So it may be okay for the first run and then not okay for the other one. But now you have modified the layout and the organization. Okay, it's the last minute change. You understood that a ratio length and diameter could be interesting. Thing about that one is called FIT end load and buckling and all this kind of stuff that come together. Comment from me, I love that you use Lego wheels. In other competition previously, it was a kind of not allowed to use Lego parts. I'm really a fan, thank you. Just great. Do you want to add anything?
No, do we want to just go through the CAD representation?
Yeah, the CAD representation is quite accurate. Pretty much everybody has seen that not modeling the wires, which we know that we shouldn't score, in reality is creating you a disadvantage rather than an advantage. Would you think that by spending a little bit more time and doing a more accurate representation, you could have saved some organization there?
Yeah, of course. I mean, if you plan like this, the wiring, we just literally just stuck it on. We didn't have any organization with it, and yeah, obviously, if you planned it out, it would have been much better. Yeah.
We also lacked the correct size thermo stretch tube. We only had too big, so it made it messy.
There is a thing that is called wet insulation, which fundamentally you can apply to it. Is like a couple of pounds, and it will save as well weight if you want to reach the stuff. Not something that you want to use every day, but is possibly useful for your next time. One of the suggestions to you and to everybody, if you are doing laser cut on the frame, it will be nice to create a little bit of holes or feature where you can run your cables inside, so that automatically you get weight reduction and the organization of your harness. So try to take advantage of the technology that you have to achieve the best with the very minimum effort in a very short time.
Actually, to respond to that, it had been planned that the batteries would be on the other side. It didn't happen because of manufacturing time constraints, but there would have been this hole to pass the wires through, which would have kind of taught them and organized them, as you said.
Understood. Thank you. Still trying to work out how to use SolidWorks.
Thank you very much.
Thank you very much. Cheers, guys. Middlesex, next one, please. Thank you.
This is my sport for the day. I may go from the 90s in the finger by the end of the day.
We opened another annex, so hopefully that won't give us any problem. Just we can try to open steps up. We will work that. All you need is like zoom in and
Now I just need to wait.
So we start talking about it. Yep. Okay, guys. Do you want to talk us through the general layout of your design, and then we'll try and get some CAD to correspond to it.
Sure. Yeah. So the driving power is applied to all three wheels. It's a 3D nylon fiber printed base, 4 AA batteries, and a circular base here for stability, which we later on applied. A foam for like impact reduction on the bottom, and a DP/DT switch for polarity switching. Fine.
Okay, and in terms of testing and design iterations, what it looks a really tidy model. Have you made any changes, or was this just per design?
Yeah, a ton. It was originally, of course, MDF. Went through a fair share of iterations, but the original design, the 3-wheel power, kind of stayed the same, but the stability thing changed throughout the course of iterations. Yeah.
And the switch reversing mechanism? It's simple.
It's the same we have used
Yeah.
since the beginning.
Yeah.
Drives its way down again.
Keep it simple, yeah.
So on your model, I saw on your presentation and then on the CAD, I saw that you were really focused on the bevel gear kind of thing from day zero, and at the same time you were focused on 3D printing. So when I looked at the stuff, I said, these guys are going into a very, very difficult challenge, because 3D printing a gear is already hit and miss. When you're 3D printing anything which is not a straight gear, is a little bit even more difficult. What made you think that that was the right design? Because there were not really a lot of evidence of which other design you evaluated first.
So we wanted to supply the power to the all 3 wheels, so it doesn't tilt or doesn't, and it should be able to lift the weight. So we wanted to give the power to the wheels. So we thought of the worm gear and spur gear before, but there is a lot of gear down in that one. So for that we have used the bevel gears. And for designing this, we have tried almost all size for the bevel gears, and once we change the design of the bevel gears, we also have to make changes to the body as well. So we have tried many different sizes for the gears.
Like mainly our focus was to change the rotational speed from this angle to this angle. So we had thought of many kinds of gears like spur gears and bevels and pinions, and finally we concluded this is the best one.
Yeah, this design journey that you are describing me is not shown in your presentation, so we just saw that your final product. So the message that we got was instead that we started with bevel gears and we finished with bevel gears without analyzing anything. So the purpose of the presentation is to tell other people that have not been with you in the journey how long or how painful or how nice your journey has been. What I understood is that your journey was straightforward. You went for bevel from day zero. You're now telling me that you did something else. 2 comments from my side. Your CAD is a schematic of your package, but it doesn't contain a lot of features that are in the real product. So I couldn't really understand really how it worked until I got to see either the presentation or the poster or the 3 things together. One comment from structural, I'm afraid that is my background, so it is what it is. So here you have a load in this direction, and you have another load in this direction. You are 3D printing something that potentially could bend this way. Have you found an issue?
That's why we used carbon fiber nylon.
Which is expensive.
Yeah, but it was fitting the budget ultimately.
Could have you done a different design for the support of these to have a better load spread and maximize the advantage of 3D printing?
Yes, we could have.
So good. In your case, you didn't model the wiring, but at least you tried to keep them neat and tidy in the middle of the device. You split the batteries between 2, which is a little bit of weight increase, but it's a weight balancing for the function of the stuff. So I think that you got for a sensible kind of development approach. Given that this is the design challenge, we would have we would love to have seen a little bit more design and a little bit less, let's build it and fix while we go along kind of attitude. So try to think about more before you build, and then when you build, only narrow down to the issue that inevitably happen. Our background is, I'm afraid, partially similar, and you cannot really design without having issues when you're in the field. But you try always to minimize those issues and really allow everybody to work with you to focus on 1, 2, 3, a number of manageable aspects. So that is a little bit of a message. So, what material do you went for these wheels? Because I didn't really. So are they off the shelf?
Yeah, we didn't make these wheels ourselves. They were just purchased the wheels.
The inside is the plastic, and on top of it, it's rubber for the better grip.
And you achieve the friction force just with the compliance of the rubber. Yeah, understood. Okay, good. Thank you very much. Look forward to seeing it ascend the tube.
I'm ready for Kingston now.
Kingston, next one. Sorry, yeah. Did you catch that?
Sorry?
Say again?
Oh, the thing with the multiple wheels, I didn't really understood how the top wheels or the bottom wheels, however you want to call them, were working. So can you please take us through the design?
So the design was inspired by a mechanism wheel, which has rollers at 45-degree angles. Originally, in our CAD model, you can see it's 45 degrees, but after testing it, we found out that 45 degrees was too steep for the motor, so we changed the design to a 20-degree slope, so the motor can power the drive easier.
Talk us through how it goes. So
yeah. So
they go in and then
they
it's
go
a
in.
helical sort of
Yeah. So these arms fold into the tube, and the motor, which is in the center, drives the central top half. Yeah, and the whole lot rotates, driving it up the wheel in a screw pattern.
So in fact, you don't drive the wheels independently, you drive the whole of that top mechanism, and that spirals its way up.
Yes.
Interesting design. Well, the only one like that we've seen today. And talk us through some of the challenges that you had. You mentioned about that angle of the helix in effect, but what other challenges did you have?
So obviously, because the top part is rotating and the bottom part is not rotating, we had to find a way to make the electronics connect. So we decided to use a slip ring idea, which we attached to the bottom, and then we attach another plate that has 2 springs and a ball bearing on top that is compressing on those 2 slip rings, and that way it can power the top part as well. Any other changes?
So another issue we had was printing out of TPU. TPU is like a hard material to print out, and sometimes it was unreliable for us. So when we were redesigning this from the TPU springs, like the bottom halves, we decided to switch back to PLA because it was more reliable to print and faster, since we had time constraints, and we opted for a spring to perform the same action.
The bottom design of the springs stayed the same, and the top one, yes, that changed.
So between the slip rings, bearings, balls, metal springs, and a lot of other stuff, I see somebody that in the spare time take apart either motorcycle, bicycles, washing machines. Did they got anything wrong, right, on these? So who plays with all these bits? Good. Oh, understood that one. Thank you for using the Lego wheels. Thank you. With this design, in the other CAD, I'm not a user of NX, so I cannot do a cross-section. But when I was reviewing it, I saw that you didn't model the wiring or other electronics. But at the same time, I believe that with your effectively self-contained organization is pretty neat. How do you change the batteries if you need them to?
So, as you can see on the CAD model, we have a bottom battery holder with a battery slide cover. And so this literally will just twist off, and you can take it apart, pull off the cover, and you can change the batteries pretty easily. Yep.
Unscrew it, and then we can take this off. Oh, wait. Hold this. And then we can take the batteries out and replace them. So the whole design is meant to be fully modular, so we can change, even if, for example, one of the springs break, we can easily take this out because they are not glued in, so we can take them out and reprint them and put them back in and fix the problem.
What consideration did you have for the mass? It's looks quite a bulky system. What opportunities do you think there is now to make mass reduction, and was that a consideration?
Yeah, so with our initial iterations, the thickness of the wall was a lot thicker than it was, so we reduced that down. When printing as well, we used an infill of around 50% to reduce the weight even more. For possible further solutions, we could cut holes into the side to further reduce mass. Thank you.
Thank you very much. Well done.
So we have one last university missing here. Can you please come forward on year one? Oh, I need to do with this now. Right. I was double checking your design. It was really complicated. Now that I see it, it appears really complicated. So talk us through the design, please.
Yes. So basically, our design works on a principle. We have a driven wheel, and when it gets to the top, we got an unlatching mechanism, which will decouple the wheel from the side of the pipe and let gravity and the chain weight pull it down the pipe. So that's the basic principle that we've gone for. We looked at multiple designs, and we when we were initially looking, we looked at one fully driven up and down with a reverse polarity switch, and then we looked at a release mechanism. Obviously, gravity works a lot quicker, so let it drop down the pipe, allow it to free fall, and that will get us down to the bottom. So we kind of sacrificed our time up as we were going to make it up, coming back down. That was the general idea.
And the battery in there, is that remote or hidden?
Not.
Okay.
We did some testing with we found these Varta 6-volt batteries, but they have an extremely short runtime, and they also don't hold the voltage. It means that we just don't have the torque that we need to push it through. The motor is 6-volt rated, like it says in the specification, but we are able to run it off of a 9-volt battery without it burning out, and we've found it's a lot more effective using that.
Okay, and your damping device on landing, an intriguing use of PPE.
Yeah, so a little bit of an afterthought. When we did initially try it, we did drop our designs from a height, and where we were going for quite a lightweight, we found that they didn't tend to break. That being said, if it lands not square on the bottom wheels, we could have some issues with breakage. Definitely a consideration for the future, finding a method of having better damping, really.
And the tension in the tube, the force is a sprung mechanism? Yep, okay.
So your design was really in one of the design where you really try to exploit as much as possible the technology of additive manufacturing. So instead of doing something flat with additive manufacturing, they can do with the subtractive manufacturing, laser cutting, milling, or whatever you kind of did there. I've seen that you have kind of lost a little bit of time in doing all these little nice fillet, and then half of the CAD was not there. So half of the journey between the CAD and the real thing was not there, up to the point where you possibly have lost a little bit of time in understanding that when you land, it comes down. Trade-off question. You said that by going up, you put on, you're probably the one with the highest number of wheels, possibly, on the thing. So there is a friction in there that you need to be effectively won by your electric motor. You have a number of wheels that are weight, and then when they come down, all this stuff could really, or could possibly slow down a little bit the descent if it doesn't come out straight. What have you learned in the journey between CAD and real life?
I would say, well, what the difference between the CAD and the real life, I think we didn't do enough in-person testing to kind of put the theory into context and understand how it's working. So maybe, so with all the different wheels, what I would do next time was offset the wheels from the drive wheels, so then perhaps we wouldn't need as many to stop it, to keep it stable.
We found on paper, calculations normally work in theory with losses, so we found spring tension, as you said, friction between the bearings. Surprisingly, this doesn't always fall straight down the pipe. We get a little bit of torque and twist just because of tolerancing and general kind of errors you may make in a cut where we've had some of the components we've manufactured. Yeah. So we did create a resin molded part. There could be some flex in that resin. So that was cast. We 3D printed a mold and then we cast it in polyurethane resin to get away from fully additive manufacturing.
Yeah. There's a lot of different things that can go wrong which need to be ironed out through in-person testing. You can't just do it all in theory and expect it to work, is what we found.
I think the lack of a self-centering point is also quite vital, because we're working on two axes here, whereas if we had, say, 3 equally spaced wheels, that would center to the pipe a lot easier. Yeah. It would give us less room to mount this mechanism for the drive wheel, but I think it's something that might be possible in the future.
What I found out is that most of the low-end 3D printer have a level in bed which is fitted on 4 points. Yeah. Then you need to pay a premium to get a 3-point attachment, which in my brain doesn't make sense because 3-point is cheaper, so why is not there at the beginning? So all the geometry, 3-point, 1 plane, always win, remember. Okay. Thank you very much.
Thank you.
Here too? Yeah, let's do it. No, I need to open this way then. Can we please have Brunel University?
Go grab it. Thank you. Just got to get it. Yep.
Oh, he's out on display.
It's out of, yeah.
And they left the thing out.
They left it. Sabotage. Yeah.
Sabotage could have happened here.
Yeah, I know. Right. Okay. Well, talk us through your design, where you got to.
All right. So
basically we have, to power our device, we have 2 DC motors here. We've then got, they're attached to a worm gear reduction with it's about 1 to 212. We basically, with the motors, they've wired to a H-bridge driver just to control them, which is then wired to the Arduino for, of course, controlling all the programming and just sending the signals to everything. We've got ultrasonic sensor at the top here for positioning to the middle, and also just when going on the way back up, it'll sense sort of when it's just past the bottom line, so we can go back up to the scoring line. So to start the device, we've got just a mic switch here, and also for detecting the top, mic switch at the top, and also a small step-up transformer here, which allows us, so we have 2 ways of controlling our speed. We can either use the enable pins on our H-bridge, or we're able to use this transformer to vary the voltage for it as well. So just a bit of redundancy, just in case.
And which one is better?
Yeah, the transformer tends to work better, yeah.
Could you then take out something if you're using only the transformer?
Well, we can, but the thing with the transformer though, so the transformer we have to change at the start, right? But with the enable pins of this, we could change that anywhere inside the pipe. So it's different uses.
Still, my thing, and probably your thing, is about the weight and the complexity. So if you really need something, just focus on that one. If you think that you need 2 things, what is the problem that you're trying to fix? But anyway, good job. You have described that you have tried to apply rubber on the wheels in different ways. Yes. Could you please take us through the CAD and the differences in all your journey in getting the rubber on the wheels?
So we went through a lot of different variations actually of the wheels, from just changing the sizing to actually fit the pipe, and also just trying different materials. Like we tried neoprene, EVA, and also rubber, which we're sticking to right now. And we found that this was the most effective so far.
Great. In your card, I've seen all that number of screws that possibly this gentleman may remember, that with that number of M4 you can hold half of the floor of a Formula 1 car. So, and then you have that one on the other side. So a little bit of an overkill. I've seen that now you're using only 4 of them. So
yeah, it became when we just wanted to take out this battery, just when we were changing things, it took too much time. Yeah.
So one of the suggested analysis of the requirement, if you think that you need to swap the battery between heat, think that is a quick maintenance because you have only 1 minute. So requirement, what is my problem? Am I draining the battery? I need to be quick. Then I think about if one screw is too much or too little or whatever, if I break it. Yeah. So try to possibly think about the opposite side. It will be over-designed, undersizing, and then you fix it if you have a problem. If you don't have a problem, let it go. My mantra to everybody, wiring have not been modeled. In your model that was looking very, very neat, the reality is a little bit less amazing, but it's still very, very valuable. So would have you done something different?
Well, yeah, obviously with our device, the wiring is quite, it's not the most organized it can be. I think we would focus on having a more better directed wiring, so that also there's not anything in the way with the pipe as well. But for now, it does the job quite well.
The consideration of weight, your redundancy, some of the design, how significant do you think that is to the success of the in the competition? Is it first order, or where did that rank?
So
somebody else.
Well, definitely it does add a lot of weight. But we are still pretty solid in terms of the timing, because of the DC motors that we're using, as well as the transformer to increase the voltage. So it does help increase the speed.
So we've got the 2 motors. So what was the choice? Why did you use 2 motors? Is that for speed? And then how did you trade the speed against the mass?
Actually, our earlier designs actually involved just one motor, and we had a pulley system instead of having direct drive. But we found, since we had to actually 3D print the gears and the pulleys to suit the motor, it didn't work as well as we imagined. So we decided to switch to a direct drive concept, which worked a lot better and is more reliable as well.
And that was a practical testing and experimentation that then led to that new design. Okay, understood.
Happy? Thank you very much, and let's look forward to see how it goes. Thank you. Can we have, please, UCLA team 2? Sorry, year 2. Thank you. He's thinking about it, so please take us through the, a lot of batteries. Take us through the design.
Yeah, so yeah, obviously we are from second year team, so we are allowed to use microcontrollers and multiple motors. So we have 3 motors, each of them running at 9 volts, and we have Arduino Uno as our control circuit. So, and in terms of sensors, we have this ultrasonic sensor that detects the distance from the top of the device to the top of the cap. And also we have this micro switch, because we need to physically touch the top. So that will reverse the device when it touches the top. But when it goes down, when the sensor, since the distance is 2.2 meters, it will go up again and stop in the target line. And that is basically how our device works. And we have the Arduino Uno as controller, and we also have a driver to control, obviously, the motors. And also it powers the Arduino, because that driver has onboard regulator. Yeah.
Sooner or later, the CAD will load. When I was looking at the CAD, and then your colleague may see it in a while, I was a little bit confused. Which one for you is the datum that we need to score? Is the top one?
Top one.
Because they look very, very similar.
Yeah.
And the drive there is direct drive. The 3 motors drive directly. Talk me through the sort of contact to the wall, the cylinder wall, and how you got the friction that you required.
Do you want to take that part?
What are you?
Basically, it's just this tapes coming from the badminton tennis grab. We're just simply using the friction and the shaping of this to grab the wall.
How did you calculate the angle, the shape of those wheels?
It's basically using the strategy of the boolean with the actual. I made a model of the tube, boolean them with a kind of a bigger wheel to get this shape, and push it backward a bit to left space for these tapes.
So we had the tube CADed in our CAD, and we projected the curvature of the tube of the inner surface to our wheel, and so our wheel is exactly the curvature of the tube, but slightly smaller in diameter, because we have this tennis grip tape that will deform and obviously grip to the inner surface. Yeah.
I see you have a LCD counter at the top. Is that to time yourself, or what's that for?
It's a distance display, and it is be count in millimeter, and it just shows what is the distance between the top and the device.
How does that make you go faster?
It doesn't make us go faster. It doesn't. Yeah, but it makes it much easier for calibration, because obviously when we point this to a wall and we have a tape ruler on the floor, and if we just do that.
On my race car, I don't put a computer on to tell me, to display how fast I'm going. It's kind of we do that off board. But I get your point. I get your point, and that's helped you in the sort of calibration and setup. Understood.
So on that subject, what I was going to add, right? So you are using your Arduino to drive an output, a visible output, telling the number that you then verify mechanically to see where you are. When you are in the competition, that additional stuff that you use for your testing is an additional complexity. So your software line could generate something that you were not expecting. Your hardware wiring may have a disconnection, the Arduino may default. Have you thought about taking it out after you did your calibration?
Yes, we could. Yeah, we could take it out, but that code was really simple because we have to calculate the distance anyway for the run. So that is just 2 lines of displaying that to the display. And obviously we could take that off, but the weight and complexity is not as much as how cool it looks like. So yeah, we would like to keep it. But if we want to go for extreme performance, we could take out that weight. Yeah.
You know my answer to that. Good. Okay, any more questions? No? Well done.
Thank you very much.
Hello, hello. Can I have Kingston team number 1 on the floor, please? And I don't seem I have your slides. I only have the video. So could you, some of you, send me the slides? Yeah? So the other ones.
Hello? Hi then, hello. Welcome to Team Masak's presentation on our design process for our internal pipe climber robot. We're going to be showing you slides on the design iterations we went through, the processes we made, and just a general overview of the group project.
Just use a mouse. Yeah, there we go.
For the robot, we decided to make the main body out of a simple. We made it a simple, sleek tube design, made out of ABS, because it provides the actual robot with structural and dimensional stability. And for most of the parts, we decided to 3D print it because of the price limit. We wanted to ensure that we don't go over the price limit by buying a lot of the things that don't need to be bought, like TPU for the springs. And we ensured to make the number of electrical components as minimal as possible. And for the size limitations, we also, for the size limitations, it was 300 millimeters and 105 millimeters. 105 millimeters long, and for the wheels, it was a Mechanism-inspired wheels. And for the functionality, the top part spins horizontally, and the bottom part is stagnant. And I'll move on to the next person.
So here you can see our design iterations we went through. So our initial design took inspiration from a Mechanism wheel, which involved rollers at 45-degree angles, as you can see on the drive wheel at the top. We then decided to simplify this design down further and mainly make it out of 3D printed parts. So as you can see in our design development, a simplified design with less rollers. And we also included a ball bearing design to increase stability and also reduce the surface friction between the two parts on the device. And then finally, we wanted to make our device more modular and include a spring design, which led us on to designing our TPU springs, as you can see on the final design, which we will now move on to in more depth.
For our final design, we noticed some issues. For example, to connect the wiring from the top half to the bottom half, we couldn't have them directly connect because as the top half spins, it would twist the wires and they will tangle up. So we incorporated a slip ring design, which is 2 rings with a top half that has a plate with 2 ball bearing contacts to maintain the connection for the electrical components between the top half and the bottom half. We also added a battery compartment to the bottom so we could easily switch out the batteries. In addition to that, we added a circuit board plate so we can house our circuits inside the tube and make it easier to wire our components together. As you can see, we have 2 different types of springs. One of them is straight, which is at the bottom to keep the bottom half stable as it moves up the tube without rotating with the entire body like the top half does. And for the top springs, they're at a 45-degree angle to allow it to climb up. We use TPU, which is a flexible filament, to make these pieces flexible so they can compress into the tube and provide more grip as it travels up the tube.
For our electronic circuit, we have a
DP-DT switch and relay, as well as a motor. The motor is connected to the relay, and once the reverse switch is activated, it will change the direction that the motor is spinning in. On the bottom right corner, we have the pin connections for our circuit, and the circuit is powered by 6-volt AA alkaline batteries. And here we have bills of materials with all the parts. Although through the testing we have not included one more button, which should be added. But overall, we have managed to design our robot under 50 pounds.
Thank you for watching our presentation on our design.
Now there is the question time. I will then. So, how much planning have you put in, and how much design, and how much execution? The presentation is the moment where we talk about that planning side of the engineering.
So to begin with, as you saw, we went through a lot of stages in CAD. So we tried to do as much of our planning in CAD first. So we had everything covered. We went through how we would get the circuit board and switch in, and how to fit the motor in properly without it damaging the internal components.
Yep. So initially as well, we'd often meet up early in the design process, and then just all of us just threw ideas together, jotted down on whiteboards, just general planning as well on Excel. And we often had team meetings every week to make sure we were meeting our steps in time for the competition, obviously, today.
If you need to put a name and a number to make really effective your job, so now you have done all the journey, you are here with your device, so it's great. If you would to say, right, I need to spend, next time I want to spend this time maximum on planning, this time maximum on design, and this time on the execution refinement and testing, do you have an idea of a fraction ratio between the three?
I would say we would put more time in testing, because we found out the most mistakes that we put in the overall design. So we would put more time in the testing.
I think we spent about 9/10 of our time with planning, and then about 1/10 of our time with actually testing it. I think the ratio would probably be something like 4/10 of our time into actually testing it, and 6/10 in planning it.
Sounds more reasonable. Any other question? Thank you very much.
Yeah, can I have Hertz Team 1, please? Is that one?
Yeah, this one. This is that one. Okay, so hello everyone. My name is Aya. I'm the leader for the Ingenium group. So, if you may, let's start from the introduction. Here you can see the table of contents. We will start from the introduction, and we'll finish from the physical prototype. So, coming to the introduction, our main goal throughout the challenge was to build and design self-contained vehicle which must safely climb throughout the 2.2 meters pipe and carry a chain attached to it. We have taken a lot of steps to finalize our final prototype. We started from the project management plan, which is the Gantt chart. On the Gantt chart, we divided our task between the group members and did everything by an order. Then we stopped at the points like product design specification, concept design generation, calculations, bill of materials, technical drawing, and etc. Here you can see that our team members, we called ourselves Ingenium, which is translated from Latin, means innate talent, intelligence, and inborn character. There are 4 members of our group. I am the group leader. I was in charge for the creative features as presentation poster. This is Edgar Rebello, who was in charge of the manufacturing. This is Zainab Stour, who was responsible for the calculations and MATLAB coding, and one of our team members couldn't come. So, coming to the project design specification, we had some definitions, limits, and specifications. So, for example, for the performance, our final prototype was designed and built to climb out inside of the piece of vertical pipe, lifting and increasing load. It must have been self-contained and have no external control except for launch switch. For example, the device must be driven by a motor rated with the maximum supply voltage of 6 watts and maximum power of 2 watts. And for example, coming to the aesthetics and finish, the transparent acrylic was chosen as a main material, and for example, the leaf springs was made of the PLA. And so we have also our limits, for example, parts from existing devices. For example, entire wheel motor assemblies were not permitted, and no pre-programmed or programmable controls as Arduino IDE sketches was not used during the physical prototype. And then let's go to the concept design generation. As you can see, everything begins with an idea. Starting from the first days of generating our ideas, we have developed a lot of sketches and drawings. Our first idea came from the truck's leaf springs, which was also supported by the spray handler's materials. So we came up with the idea of locating 4 leaf springs in our physical prototype by each side of the wheel. And now we can continue from Edgar, who will more talk about the manufacturing processes, the materials we used, and the manufacturing.
So we tried to do something very innovative. So we really wanted to go with our leaf springs, and we had to think of a way we could integrate this with saving space for our board, batteries, wheels, and while still maintaining its light weight. So we decided to go with the 4 springs, as Ayas just said, with the 3 wheels. One being the driving wheel, and then the other 2 are more for support. For energy storage, as you can see, we have our inspiration, which came from the truck leaf springs, and from the handles, from some spray bottles. We can see now these are available in the market. You can see found in flash bottles as well. There's only plastic used, no metallic pieces whatsoever. So we tried to combine the 2 ideas with the combination of our slots, as I said before, so that the leaf springs can flex effectively. On the bottom, we have some of the dimensions of the springs that we used. These are the dimensions that we found most effective, that didn't give so much friction and allowed the machine to move freely up the pipe while still maintaining its weight. For the reverse system, we have a DP-DT switch, which basically just touches the top and reverses the polarity of the motor, allowing it to come down freely. And for the control mechanism, we just went with a simple on and off switch. For the power transmission, we went with 4 1.2 volt batteries, and these gave us the best weight to power ratio, allowing the machine to move effectively.
When it came to the calculations, we decided to use MATLAB to help us out with it. With MATLAB, we were able to calculate things such as the radius of curvature, spring deflection, extrusion depth, and the leaf spring thickness. As for the mass and length, we managed to calculate that the mass was 379.4 and the length was 300 millimeters. When it came to the bill of material, we mainly focused on things such as the budgets and the material we had at hand. For the material, for the frame of the material, we used acrylic, and for things such as the 3D printing the leaf springs, we used PLA material. As for the screws, the motors, and the wheels, we were provided with them by the university. The limited budget was £50, whereas the total cost we spent was £39.15.
And after we made the virtual model, we stopped to do the technical drawing. Here, as you can see at the right bottom side, you can see the part numbers and the names and how they were manufactured. Most of them we made in-house at the university using the all needed equipment as laser cut and 3D printers. Afterwards, this is our final physical prototype. It has the leaf springs, the PDT button, motor, coupling, aluminum wheels, and on-off switch, as you probably seen before this. And here there are QR codes for the presentation and the poster. You can scan it, and if you want to see them more closely. So that's it.
Thank you very much. I really enjoyed going through your presentation when you were, when I was doing the evaluation. A couple of things. One positive comment from me. You did a nice assembly drawing with the table, that is your bill of material. That is a good way to link what you need to do with what you're doing in CAD and getting a nice job out. And the product that you brought in today is a good example. So your design was accurate and your product was accurate. I've seen that you have spent a lot of time in calculating the leaf springs because that was one of your key. I haven't seen a great deal of the other calculations, so friction of the wheel on the tube, acceleration, torque needed for the motors, gear reduction, name it and have it. So I've seen that you really went into the leaf spring, which is an admirable task for a student at first year, but then you kind of lost me if you have done anything on the first principles of engineering of the device. One of the three?
Well, since we went with something very innovative, we did spend a lot of time calculating the strengths of the leaf spring. That took really a lot of time. Do you want to talk about the calculation? Okay. Unfortunately, the person who did the calculation is absent today, so I'm not very aware of that area. I have very basic understanding of that area, but I can't really answer to you.
Thank you very much. Let's see the challenge later on. Cheers.
Yeah. So can I have UCL first year teammate ready, please?
As a group of engineers, our challenge was to design an internal device that must climb up and down a pipe, all within a strict budget of £50. We must also make sure we're carrying a chain throughout this entire motion. Here you can see a short summary of our design journey. We initially started off with a symmetrical four-wheeler, but then quickly transitioned into a free-wheel device with one large driven wheel to increase the torque. We then decided to implement springs into our device to increase the normal reaction force within the pipe, helping the device climb smooth up the pipe. We also decided to rotate our motor such that it is vertically within the pipe to fill space efficiently. Now, all of this led to our final iteration, which you can see here. Here you can see some isometric drawings of our device and the full CAD. So we're using a 4-pack of AAA batteries with a 1.5 volt rating, which is different to our initial 6 volt alkaline batteries. We found that they were 7 times more efficient in that capacity. And here are some short design justifications. So we've got a vertical orientation to allow the motor itself to be used as a structural component. So our motor, we're bolting on the plywood sheets to sort of wedge the motor in. We're also using stabilizing wheels to prevent tilting within the pipe, and some polyethylene padding on the bottom as well.
One of our design objectives was to ensure that our device was as light as possible. We initially set a target of 200 grams, and we achieved this target as our device weighs 151.8 grams. Here you can see a breakdown of our estimated weight and the components used to build the device. Our battery pack takes up the most weight, but we were able to make this compromise to ensure that enough torque was produced to accelerate the device. This also helped with key design decisions. We initially compared different motors and their performance in the pipe, and we found that a single 200 RPM TT geared motor should be used to power our device. Our motor has an internal gear ratio of 48, and to optimize the torque transferred to the wheel, we plan to use 2 3D printed gears with a gear ratio of 2 to further improve the time taken to reach the top of the pipe.
One of the requirements of a climber is for it to return back down to the datum once it reaches the top. We had 2 possible ways to do this. Either have the motor turn off and for the climber to roll back down, or have the motor reverse direction. We chose the second option, as in this case, not only is the climber's weight pulling it back down, but it's also driven by the motor. To do this, we attached a DP-DT switch to the top of the device. Once the switch is closed, it reverses the current in the motor, effectively reversing the motor itself. This is shown by the circuit schematic on screen. Our device has 4 wheels. The largest 30mm radius wheel is driven by the motor. Our Excel simulation has shown that this radius allows the device to achieve the shortest possible time. The second wheel with a radius of 20mm is used to increase friction, and so increases the acceleration of the device up the pipe. The 2 jockey wheels behave as stabilizers, preventing the device from tilting and scraping the sides of the PVC pipe. We also implemented a spring mechanism to improve the stability and control of our device. We compress the spring and insert the device into the pipe. Upon releasing the spring, the normal contact force on the device increases, and so increases the friction, preventing the device from slipping. We also implemented a small swivel clip securely fastened on a bolt for the chain attachment. This clip will be slightly offset from the center to ensure that the center of mass of the device is closer to the middle.
One question we needed to investigate was whether our device slips when put in the pipe. 2 conditions need to be satisfied. We did calculations and found that the weight of the device is less than the maximum total frictional force, and the vertical force accelerating the device is less than the maximum frictional force per wheel. So these conditions were satisfied and our device theoretically worked. We also used Excel to simulate our device's performance in the pipe. We plotted the vertical position against time and the vertical speed against time, and found that our device should theoretically reach the top of the pipe in 13.1 seconds. Thank you for listening.
Thank you so much. When you did your calculation and you were talking about the mass, and you say, right, I account for the mass to see how long it will take to go up and down. Did you account as well for the mass of the chain that you're dragging with you? Okay, that was not clear in the presentation, but it was clear from the graph. So the graph were not linear, so you would kind of assume that your mass was changing by doing the journey. Compared to a normal, let's say, 1 year lecture or year 1 lecture or whatever, having variable mass in an exercise, is it something that have you find interesting, or you know, comparing, you know, friction is almost constant, or you want to have it constant, but your device or your torque was driven by a changing mass or a changing load that need to do?
I mean, in our Excel, we've modeled the chain, the mass of the chain as it goes up. So the mass of the chain increases. So I think in our presentation we put the maximum frictional force, and we've got an appendix to show all the calculations that we took. So in theory, with the chain and with the motor specifications, our device should work in theory.
When we were checking the CAD and the real thing, you talk us through the journey and the differences and everything else. I've seen here that some axle have effectively a D-cut, and instead you bought off-the-shelf wheels that looks to me they have like a plain round bearing shape inside. Have you found any issue in slipping or not taking advantage of the D-cut in the axles to transmit the torque to the wheels, or it was okay, just the press fit?
Yeah, when we had we used stainless steel rods, and we filed it into a D shape, and it worked pretty well when we were testing, and we didn't really encounter that many problems.
We also had to 3D print our gears, and on the CAD we had to experiment through many iterations the actual shape, the whole expansion shape of the D shaft. So through many iterations we eventually got the perfect size for the gear to just slot on and not move on the actual shaft itself.
Good, fantastic. How much time have you spent in really detailing everything for the BOM and throwing it in the presentation to calculate how much it costs, how much it weighs, and then double check that your weight is in line with your product?
Yeah, we distributed the work throughout our team members, so we had a few people working on the BOM, and we kept constant communication in between each other to ensure that the BOM and the presentation all matched together. And yeah, whenever we made a little change, we always updated the CAD, we always checked the weight again, the price again. So yeah, we kept on iterating that process and kept on updating everything as we did it. Yeah, thanks.
Okay, since we only have 2 second-year teams participating in this challenge, so can I invite Brunel team, second-year team, to do the presentation, please? Yeah, you only have one file. That's the one. Yeah, just.
Sorry, one of our group members is just going to come back. Yeah.
Okay, so because we have one team member missing, so can I have the UCL team then? So you, yeah. Yeah.
deliverables slides.
Hello everyone, we are Team UCL. In this presentation, we will introduce our internal pipe climber design. Hope you enjoy. Our presentation will include the following 8 sections: iteration, structures, climbing mechanism, positioning, followed by remote homing, which is our innovative features. Then safety and details, cost, and finally the performance.
And the biggest problem of our original design was that the power just not enough and the friction was too much. So in version 2, we added another motor and we changed to a triangular design and also added idle wheels to reduce the friction. And in our final design, we switched to a more efficient driver and larger batteries. Also, we went to a sandwich layout for the space optimization. And also we reduced the use of plastic and changed this component to more environmental friendly materials such as plywood. Also we reduced the number of wheels from 6 to 3. 3 wheels makes the whole device more stable. Yeah.
The powertrain is consist of 3 12-volt motors, each running at 200 RPM after reduction gear. And each motor is paired with a wheel that is designed to fit the curvature of the tube. And the tires are made of polyurethane, and that is obtained from rocket grip tape. The equivalent diameter of tire surfaces is slightly greater than the tube's internal diameter. And the tiles will deform to exert normal force on the tube to grip the surface. We have also added 3 small idle wheels to prevent the lower part of our design from scratching the tube.
Yeah, in terms of positioning, as mentioned earlier, we have this ultrasonic sensor that allows our device to calculate the real-time distance of our device to the top of the cab. And in terms of running sequence, we have a switch at the bottom that will start the device and go to the top and actuates the top switch and then go down and go up again, stop in the middle. And yeah, and that is our running sequence. And we have our innovative feature to avoid the hassle of pulling the device out after stopping in the middle. We have added a magnetic switch that will allow us to remotely control the device to come down, and we can obtain that easier. Yeah, and in terms of safety and details, we have included blade fuse so that in the unlikely event of shorting, we can protect our driver and our board. So, and we used 8 1.5 volt AA batteries to obtain a total 12 volt power. And we have protected all of our terminals with hot glue so that there's no exposed terminal, also to reduce the risk of shorting. And we have hand crimped all of our DuPont cable, so DuPont wires, so that the cable management is the cleanest, and also we have easy access to all of our components.
Let's go into the final cost. Our total cost is 60.73 pounds, and our IMechE relevant cost is 55 pounds. With our top components is electricals, controls, and batteries. And consider the total cost is relatively low to the other funds, it would be 100. We still have a lot of potential to enhance our design, like lighter materials, powerful motors, and better batteries. And it's common. I think it's common way that using a less cost material during the engineering process. Our final runtime will be 20 seconds, and our target reference around the final line will be 3 centimeters. And that will be all our presentation. Thank you very much.
So on the year 2, there is 2 and another team competing. How are you feeling?
It's not surprising because we saw the schedule that our time was very short, so we know that there isn't many teams competing. But also that the second year challenge, it is more challenging. And yeah, it's good that at least we have some team to compete with, because last year the second year challenge had no team to compete with.
Oh, you're raising the bar here. So I've seen in your presentation and your design that you really enforce the concept of the curved wheel to kind of mimic or adapt to the pipe structure. Did you? Yep. Okay. Did you consider that the pipe is a real, industrial product where it may not really be round? So did you consider in your compliance that the pipe could change in diameter and change in shape?
As we can see from on the top of the wheels, there is a grip tape, and this tape has some electricity, and it elasticity. Sorry. And it will deform, to fit the curvature, and it will give the tube a normal force to grip the surface as well.
Good. Now that we are in the year 2, we can challenge a little bit further. So you have 3 motors, you have 3 wheels that have some compliance. Compliance means that the part of the torque of your motor will have to deform your rubber, and then that energy is kind of lost. It requires then more torque than potential and alternative design with 2 wheels only, or 1 traction wheel and another stabilizing wheel. Did you consider this in the overall concept of mass or layout of the competition?
Yeah, so as we saw in the iterations, initially we only had 2 motors. And yeah, that 2 motors, we could still reach the target, but the torque would not be enough. And by adding another motor, and we can also see that although we increase the number of motors, we decrease the number of wheels. That is to reduce the loss of from the friction and also that deformation. And the increased power would be much more than the loss by that increased motor and wheel set.
We had a chat before where your CAD and your real product are a little bit different. How much of this difference is, how can I say, accounted into the BOM? So how much did you realign the BOM to say, right, I really build with this stuff, so my real cost is this, and why did I not consider to put everything in CAD or whatever? Was it, so the 2 things?
What do you mean, what difference in CAD?
BOM, real product,
yeah.
The 3 things in theory should be aligned.
Yeah.
Which one did you decide to sacrifice and why?
To be honest, we didn't sacrifice any. In our CAD, the only thing we have sacrificed are the 2-pound wires, and everything else was CADed as seen on the picture. Every single bolt, every single nut, every switch, everything was CADed. Even the gear inside the gearbox is CADed. And I don't think we have any sacrifice in terms of the BOM. And yeah, and also in the BOM, everything was in the BOM. Even the wire, even the, yeah, everything. Even the washers. Yeah, it has everything.
In a different time where you submitted your presentation, because your presentation is a little bit more accurate than your 3D CAD.
Is it?
Yeah. The CAD that we evaluated was slightly not exactly this one, but that's fine, no worries.
What specific difference could you?
The battery pack was not really fully detailed, and some fixings were not there.
It is there. So we have this fabric thing. It is. In the CAD, yeah, in the CAD we have this 8 battery tray, and also in the CAD it was blue, but in here is red. It's a Velcro tape that.
Oh, okay, got my work wrong.
Yeah. So yeah, so on the CAD we have that fabric thing. Although it's not fabric, it's Velcro, but they do the same thing. Yeah. And yeah, and this presentation, this render is based on CAD and it's 100% accurate. One thing that the quick link at the bottom on the CAD, it's a threaded quick link, but here it's a elastic one because we just found the random one from the workshop. Yeah. Thank you.
Thank you very much. Can I invite the Brunel team to come down again, please? Yeah, it will take some time to open.
Hello everyone, welcome to our IMechE design presentation. So in this we'll mainly be discussing the main features and all the iterations we went through for the design of our internal pipe climber. Now, for us to reach our final design, well, of course we went through many different iterations. With here presented is our very first initial concept, and in this we used a pulley system which was powered by just a single motor. But on some further advice, we were warned that just through the system, many errors could have occurred as each of our pulleys, as you can see in this, they're of different lengths, and these differences could have caused quite a bit of instability and varied transmission to the motors as it was going through the pipe. And of course, this just resulted in the non-linear movement and possibly falling out the pipe. So we mainly for our next design, we focused on this and tried to improve this to make it just a lot better. So, in this, most of the attributes were kept the same. However, there's now an added button, and both pulleys are of the exact same length to try and remove that sort of varied transmission. However, the main problem with this one was that all of our gears had to be 3D printed, as they were all of like a very custom size due to the unique layout that we have in the system. So this resulted, when we had printed them, this resulted in the pulleys just having bad fits on the gearings just due to errors in the 3D printing.
So, so as you can see in our next model, we basically got rid of our pulley system and introduced a direct drive concept. And this basically consisted of 2 wheels with each of their own motor, DC motor. And at the bottom of our device, we have a hook that allows us to easily attach and detach the chain. And the problem, why we got rid of the pulley system was because there was problems with the belt tension and also the teeth fit. And we did have issues with this new model as well, as the electrical components and the wires of the device couldn't fit in the body of the device, so we had to alter that as well.
Due to this, this led to a newer version of the design, which had a more elongated body to suitably house the parts and all the components. We additionally made further developments on the wheel, because during our early initial stages we had a lot of problems with traction and traction across the pipe. These alterations range from simply enlarging them, the wheels, and sometimes just reducing their size, to sometimes completely changing the materials of them. We decided to go along with ASA, with liquid rubber inserted onto the wheels, which gave us properties that were required, as well as it lets us to experiment with different sizes, shapes, and it's a lot easier to change in terms of the wheel sizes as well as the rubber. The option was also cheaper in comparisons with TPU and other standard parts.
For the body of the device, we had a range of materials to choose from, and after examining the properties, we chose ASA, and that was because it was a good compromise between the properties of ABS and nylon, and it also had the ease of printability that PLA has, and it also has the advantage of having the lowest density out of the 4 filaments, which reduce the overall weight of the device.
So our final design consists of 2 DC motors in direct drive, and the directions are controlled by the H-bridge driver. And there is an ultrasonic sensor attached which can enable distances to be measured, and the motors are programmed to react to these distances accordingly, whether it's at the datum line or at the target. We also have 2 buttons in the device, so one at the top reverses the directions of the motors, and one at the bottom also it acts as a low voltage starter. And we have space to attach and detach the chain at the bottom with a simple mechanism, as you could see. And we also have enough space for all the components and electrical parts to be fitted within the device.
So the initial switch starts the motors, which is at the bottom, and it moves the device upwards. And when it reaches the top of the pipe, the button is pressed at the top, which reverses the motor's direction. And once the device reaches the datum line, the ultrasonic sensors detect the 2.2 meter distance, and it causes the motors to reverse again and ascend. And then once the sensors detect the midpoint, which is the 1.1 meters, the device stops.
So for the engineering science of the device, we also had a few assumptions, and one was that we had a constant RPM of the motors at 62. We also assumed that the wheels were in constant contact with the sides of the pipe at all times, as well as having the current and voltage supplied to the motors be constant. And we also assumed that there was no slippage in the pipe, which is not always the case.
We then calculated the device's operational time to be 2.45 hours, and this was only from a single charge, using the specified charge for the battery and the current for the motor. After this, we then calculated the frictional force exerted on the device, and then from there we determined the turning force using the torque from the motors using the specification and the length of the wheels. And afterwards we calculated that the resultant force was 0.707 newtons.
So another estimate we needed was the time to complete the challenge. So for this, we found the actual force that the motors were pushing the device with from the RPM that we were using. Now, of course, we can then find the acceleration as shown here. And from all these calculations, we were then able to approximate the times taken for each stage of the device throughout the competition, and this totaled to be 41.38 seconds.
In order to reduce the cost as well as the weight of the material, we made areas of the ASA materials hollow where casing was unneeded. This was due to also reduce the cost as well as the weight of the actual device. On testing, the ultrasonic sensor enough was needed, so we didn't really need color sensor, so we just removed it.
Yeah, and on top of this, we also have the 2 worm gear motors that actually act as part of the structure of the device, so that reduced some of the printing costs. And on top of this, we also have custom-made wheels, as you can see, which are a lot cheaper than ones on the market if you were to buy proper wheels. And the total cost came out to be around £82.30. Thank you.
So it's looking like you spent a lot of time in analyzing the physics or any principle that you could understand before taking a decision. At high level, in this competition, we have seen 1 motor, 2 motors, 3 motors. Each of these has a benefit. Each of these increase the weight. You cannot say that 3 motors are lighter than 1, but they may go faster. So where is your trade, the point where you say, right, I went for the two motor independent, assuming that, or accepting that they may or may not have exactly the same speed, and I'm happy with the design and the efficiency and the speed.
Okay, well, so to address the two motors just going out slightly different, well, why originally we swapped out the one motor just because with the whole pulley system, it just wasn't possible. So then, of course, for the two motors, you said something about them having the different speeds. However, throughout our testing, we've been sort of measuring, since when the H-bridge is starting up the motors, it's of course sending a voltage to them, and we're able to tell the difference in speeds just from the voltage that each motor is getting, and the difference in voltage is only 0.1 volt at most at times, so they're almost running at exactly the same speeds. The main trade-off with the motors we're using right now is due to how high torque they are, we've lost a bit on just speed, as we are running at a far lower RPM than our competition at the moment. But to compensate for this, we can, as with our transformer, we are able to slightly overvolt the motors just to increase that speed and to maybe cut down on the time that we're going at.
So you're racing with the transformer then? I've seen that you went for this D-shape cut and everything else, and then we discussed already about the number of bolts and the other bits that are there. You discuss a lot about reducing the weight in the PLA, which is one of the lightest part that you are making, because you can contour your 3D printing to the function that it has to be. Where do you think you could have been better for the weight? Or looking from another perspective, which is where somebody else is used to do on a daily basis. You had a budget of £100, you underused your budget. The budget, if you were using 99.99 £99 and 99p, nobody was telling you that you were any higher or lower. The budget is the only thing that in the competition doesn't count. So it's there, but we don't rate you on that one. Do you think that by using that extra 12 quid, you could have had any benefit?
Well, first, you talked about the weight and how we could have maybe improved that. Well, for our design, we weren't really able to use many other different components because of the mechanism of our design. So this is the components that we used, we stuck to them, but we tried to work around that by reducing the actual structure. In terms of what we could have actually improved on, I think we could have actually added some more maybe we could have added a slightly smaller motor if we had the chance and have more a higher number of motors. Is there anything else you want to add? Yeah. Okay.
Thank you very much.
Thank you. Could you take so? Yeah, so thank you very much for the teams, for the presentations, and for their answers. Now we finish the first half of today's event. So from now, feel free to grab the lunch, just where you saw the coffee and pastries. And during the lunch break, can I ask you all to go to the registration desk to grab one of you a peer review sheet, and for the judges, could you also go there to grab the scrutinizing sheet. And during the lunch break, make sure that you have at least one team member standing right beside the display board to answer any questions. Okay, and we'll start the actual competition at 1:45. Okay, thank you very much. Okay. Actually, it's actually from last year because of the launching, but yeah, just it's fine. Should we leave him? Yeah, leave him. Thank you. Okay, thanks for coming back. And as scheduled, we are starting the actual design challenge now, and we'll have the first year first, and then the second year. Okay, in the first year we have 9 participating teams, so we'll have the qualifying run first, and then we'll have the second year, which is already final because we only have 2. Okay, so we'll have the first year, then we have the second year, then we have the first year final for you to, replace your batteries or whatever. Okay, so on the big screen, you can see the first round. Can I have Imperial Team A, London South Bank University, and UCL Team A to get down here, start preparing your device, please. Thank you. Oh, yeah. Yeah, and also, can I remind you to submit your peer review sheets to Emma as soon as possible. If you haven't done it, please do it. Yeah, thank you. Yeah, it's the first year we don't have to take pictures. Oh, okay. Yeah, only the stopwatches.
Oh, okay. Yeah. Do you have to write any team names?
Yeah, yeah. Oh, you already have it, yeah? So just give it to Emma, that's it. Yeah.
So it must be missing a team because Hertfordshire. Oh, that's just Hertfordshire 1 and 2, isn't it?
Yeah, yeah. Oh, yeah, sorry, yeah. 1 or 2. Sorry, yeah. Yeah, okay.
Thank you. We've just got a record of it, so Vin and I are going to film the actual bit so that.
Oh, I see. That's fine. Yeah, absolutely. Yeah. So we're going to need the stopwatches.
We're just doing some.
Oh, okay. Yeah. That's great. So you should have 9 for the first year, right? So first year, yeah? Okay, so Hertfordshire Team 2, you have not submitted your peer review sheet. Can you do that as soon as possible, please? Yeah, to Emma over there, yeah?
If we sort of stun it, if we double check that we've got stun screen area for the teams.
Yeah.
Brilliant. Thank you very much.
There is, but these engineers haven't got a sense of humour.
Oh, okay.
That's not true, Alan. No, I am. Well, that's what downfall my sense of humour.
Paula. Paula, sorry, do you mind grab the this one of the tubes? Yes, we.
One operative per team. Rest will step away.
Yeah, I will. Okay, so can I have the second group, which is Kingston University A, UCLB, and Hertfordshire Team 1, please?
First of all, to weigh in as well, please. Do we weigh you first?
Yeah. Oh yeah, please come here to weigh your device. We have a scale. Yeah. Yeah, so it's Kingston A, UCLB, and Hertfordshire 1. What do we have? ICA.
Big E is in Kingston. Well, no, we can knock 200 grams off that next time. Easy.
Hold on, this should be calculated. Yes? You have a chance to repair your device, but do not touch the pipes. Yeah.
Yeah, you can stay in this area, but when doing the attack, you have to stay back here.
That correlates exactly what it can. It's just 5 grams lighter than projector. That's what I meant. A lot. 5 grams is a lot.
Right.
Ping table countdown. Ping table countdown at the end of a minute. Say stop
You always respond for the leftmost. Yeah. Okay. Sorry, touch what?
Are you allowed to catch it when it comes down? I don't think
No, you're not. You have to drop it.
That's how the whole point of the design.
Yeah. So once you switch it on, you're not allowed to touch it anymore.
They can turn it off when it hits the floor.
Oh yeah, after it hits the floor. When it passes this line, then you can.
Yeah.
Do
When
whatever.
you hit that, when they say start, I've explained to him and
Yeah.
you explained to the engineer.
Yeah. Yeah. Okay, just to re-explain the whole thing with them. Okay, just. Yeah. 'Yeah, just to reiterate, I will have 1 minute preparation time, and when I say stop, don't start your device. Yeah, after that, I will say 3, 2, 1, go, then you start your device. Okay? Yeah, there's like a several seconds gap in between. Okay? So now, if you could start your get ready for your preparation. Your 1 minute preparation starts now. Raise your hand when you finish. Yeah, good. That bottom blue line, yes. Fifteen seconds left. 8, 5, and you should stop now. Okay, so I will say 3, 2, 1. That yeah, just really quickly. Hold on, how do I reset this? Okay. So, okay, now I will say 3, 2, 1, then you go, okay? So 3, 2, 1, go. Yeah, you can't touch it. So you have to wait for the next round. So it didn't touch, no.
The tube is bigger.
No, we made.
It is. We'll try another tube.
Yeah, that's why we have that 3 attempts.
Do we end its misery or?
If you want to report, Okay, so nobody. Okay, we can. Okay, so can I ask the team to stop it and swap pipes, please? Bring the label with you. Leave the chains. Yes. Okay. Start to swap pipes. Whenever, let's say this one. Yeah. Then he goes that one. Then I go that one. Yeah, if you you can go to the left. Okay, so yeah, you go to this one, please, and you the middle one, and yeah, can I ask you to go to the right? Yeah. Either this one or this one. Yeah, put the thing down. Okay, so you shall have your 1 minute preparation. Yeah, can I ask you to? Yeah. Okay, so 1 minute preparation starts from now. Okay, 30 seconds. Fifteen seconds. 5, 4, 3, 2, 1, stop. Yep, please. Yep. Okay, now I will say 3, 2, 1. Okay, so your run starts 3, 2, 1, go. Okay. So can I ask you again to swap another pipe? Which one did you do the first? Okay, so these two, it's up to you. Which one you want? Maybe this one? So yes. Yeah. So technically, yes, we should. Yeah. I can ask you to. Yeah. Okay. So which two did you do before? You just need to select another one. Yeah. Which one did you use before? Use this one, this one?
No, we're not using this one at all. If you go to one.
Okay, so you will have your 1 minute preparation starting from now. Thirty seconds. Okay, 10 seconds left. Okay, stop. Okay, so now 3, 2, 1, go. Oh yeah. Probably this is.
Remember, he gets about halfway in the stop.
The tube is not the same as the one we had at UCL.
We can have a caliper to just test it. That's fine.
Because we had
Yeah.
to sand down the wheels because it was too big for the other one.
So.
Okay. I'm just conscious of all the work you put up there. And we,
Yeah. Okay, can we give a round of applause for the 3 teams, please? Can I ask the last first-year teams, Hertfordshire Team 1, Middlesex Team A, and Imperial B, come to the back of this rig to do the weighing first, please. Oh, sorry, it's Hertfordshire Team 2, sorry. Why? I saw you change it. Yeah. Oh, that's why. Okay, my mistake. So you need to. Yeah. So now. Is the wire included? Philip, sorry. Would you mind taking the weight, please? Thank you. Sorry? Can I ask the three teams to select a pipe? Yeah? So bring the labels, yeah. Okay. So your 1 minute preparation time starts now. There's 30 seconds left. Fifteen seconds left. 5, 4, 3, 2, 1, stop. Okay. So now I will count 3, 2, 1, then you go. Okay. 3, 2, 1, go. Ooh. Woo! Hold on. So yeah. So the first time Middlesex University A takes 17 and 87 seconds. Sorry, how much? 24.1. 24.1. Okay, can I ask you to swap pipes? Yeah, stay with the pipe.
Datum is the bottom line.
Yeah, the bottom line, yeah. So those two upper ones for the second year is 10 mil parts. Yeah. Okay, so have you selected the pipes yet? Okay, okay, so your 1 minute preparation starts now. Oh, yes. 15 seconds left. The bottom blue line. Yep. 5, 4, 3, 2, 1, stop. Okay? You should, okay, 3, 2, 1, go. Okay, so can I ask you to swap pipe again? Thank you. So it's only fair. Everyone try this pipe, yeah. So you haven't tried it, yeah. So you go with this one, yeah. It's only fair. It looks like this one is. So yeah. So you just choose one that you didn't, you haven't done it, yeah. Okay, have you taken it out yet?
I've already used that. Yeah, so no, you need to use this one. Yeah.
Okay, so could you just go to the rightmost?
Yeah, if you could use
Yeah.
2. Yeah. And Imperial, if you could use
Yeah,
4.
use that one. Yeah, exactly. Okay, your 1 minute preparation starts from now. Yep. 20 seconds left. Five, 4, 3, 2, 1, stop. Okay, so 3, 2, 1, go. Okay, so I will take your one.
Twenty.
27, 28.
So that's half a share, 2.
Okay, so far we've completed all the first year teams. Yeah, so can I invite the second year teams to have come down and get prepared? Can I ask you to come down to weigh the device first? Sorry. Yes, yes, yes. Yeah.
So when you go to the tubes, okay, you'll move to the tubes, you're going to get a minute prep. Pinko will say when that starts. At that point, you can attach the chain and put it in up to the first blue line, no higher. He'll say stop, you have to move your hands away, you cannot readjust. He'll then do 3, 2, 1, and at that point you can turn it on. You've got 2 minutes to go up and down. You cannot catch when it drops unless you're withdrawing. Okay?
All clear?
And only the operation at the tube.
So weigh your device so I can take the notes.
Does this reflect the weight on the bone? Because
That's what we check.
so on the bone, our weight has 260 batteries.
You see, your weight So now we're going to start the second year competition. So just to reiterate, it will stop from different starting lines. So first attempt is this line. Second attempt is this line. Third attempt is this line. Yeah? You should go all the way up, touch the top, comes down below the datum line where you started, and then stop wherever you can. Okay? So your preparation time starts now. Sorry? Yeah, yes, I would do this. Yeah. So you not only swap tubes and also different starting lines. So each time they should return to where they started and then go back up again. Yeah. And
Where are they starting the first one?
at the bottom one, yeah. And we have the bonus point wherever they landed. Yeah. 20 seconds left. Make sure the datum is okay. That's fine. Yeah, yeah. Okay. 10 seconds left. If you're all ready, I'll just yeah. Okay, so 3, 2, 1, go. So I will do this. So that's 10. Good job. Good job. Okay. So what is the second? 25, 25, 50. Yeah. Excellent. And that's 10.
10, yeah. Right on the middle.
Brilliant. Good job. Okay, so can I ask you to swap another pipe? Leave the chain. Yeah. Whichever you want. Not the one you tested. Yeah. Leave the chains with the pipe. No. No. Okay, so your choose one. Choose one. Okay, so already yeah. So your 1 minute preparation time starts from now. That's a recharging the batteries. Thirty seconds left. Oh, the second one, the second line, the blue. Yeah. 10 seconds left. Okay, looks like you're ready. 3, 2, 1, go. I'll be timing this one. Oh, it's a bit, here it's a bit, we need.
I think in the rule it says if you cross 2, it takes the higher one.
Really?
Yeah.
Okay. So how, anybody higher I can, yeah, I think what you, yeah.
Well, that's my picture.
So it's 10 then. Yeah.
I think in rule it says if it crosses both lines, it takes the
It's
higher
the higher
score.
one?
Yeah.
Okay. So you're obviously in between 10 and 8. So, okay, 10. Okay, so can I ask you to swap the pipe again? Okay. Yeah, I'll take the note of the timer anyway. So, but no bonus point then.
No, exactly.
Yeah. Okay. Thanks. Paula?
Do I use more voltage or you?
So which one do you select this? You were on, oh, you were not. Okay. Yeah. So your 1 minute preparation starts now. It's like those F1 races. Oh no, they are. Oh, I see. They are upgrading the code because a different. Yeah, because a different distance. Yeah. Oh, I thought they were charging. Okay. They're actually upgrading the code, I believe. Yeah. Yeah. The up. So 20 seconds left. So you all ready? Okay, so 3, 2, 1, go. That's, oh, sorry, that's 2 bonus points. So that's 2, 13. Okay. Yeah, so I think we finish all the runs. So I'll go to the next. I need the outline, sorry. Okay, so thank you for the ones who participated. I know some results might be disappointing, but well done for all. And now, the judges, we will need to have a discussion. And please make sure you stay around. There will be coffee, and food outside. And we'll gather you all together to have the winners announced. Okay, thank you. I will. Yeah, the 4 teams. Okay.
What was the timing for the other teammate?
Sorry, we were having some discussion. Sorry. Sorry, guys. Can we invite you in because we are going to have some finals. I know that only 2 teams completed tasks, but by rules, we still need to have the finals. Okay, so you get ready. Okay, so can you all come in, please? Yeah, can I have your attention, please? So by IMechE rules, although we only have 2 teams from the first year who completed the task and 2 teams from second year who completed the task, but by rules, we still need to have the finals. So the finals will be, the finals will be happening between the 2 second year teams and the 2 first year teams who completed the task. Yeah, so can I ask the first year teams, Middlesex, and use Hertfordshire team 2 and Middlesex team to get ready, please. And this time we're only going to test on 2 pipes, not 4. Okay, so wait until we tell you which 2, yeah? So attention all the teams, this and that with the red and green buzzers are the tubes you're going to test the finals, because it seems like these 2 are a bit out of the tolerance, as you say. Okay, so these 2 are the ones we're going to test, okay? The team, yeah? Okay, sorry, another change of route, sorry about that. So it's going to be 3 runs for the second and first, so this is additional 1, yeah? So 1, 2, 3, because we need 3 runs to calculate the score. It's in the formula. Okay, thank you. So can I have the Hertfordshire team 2 and Middlesex team to get ready, please? Okay, so can you gather around to, so forget about this pipe, okay, for now. Let's do these 3, and you're going to all test all the pipes again, yeah? So can I have the, which university are you? Middlesex. Yeah. Okay, so, yeah. No, the other. I'm looking for the other one. Where is it? So your team is missing, Paul. Yeah.
I don't know where my screw is.
So can you do the run or not?
I need the screw for this.
And where is it?
I've got another one.
Okay. Okay.
What's that?
He's missing a component. Dropped. Yes. Although two teams, but you just do all the three pipes.
Perfect. And then we do the
Hopefully they will. For the second year. Should be fairly quick.
I looked at the Gibson design. It was lovely.
Yeah. I like it.
Great, yeah.
Ready? Ready? Sorry? Well, you have to complete the task to have the time. And then who's the fastest? Yeah? Okay, okay. So we only need actually two people to do the timing because two teams. Yeah, it's fine, yes. Okay. So you will. Okay, so yeah. Okay, I will do this one. Okay, so your 1 minute. Oh, sorry. Welcome to the finals of first year IMechE Design Challenge. And we have Middlesex University and Hertfordshire University Team A. Okay? So the rules remain the same. Okay, so your 1 minute preparation starts. Sorry, yeah. Okay, so your 1 minute preparation starts now. Raise your hand if you're ready, so I know I can stop the watch earlier if needed. All done? Okay, good. So 3, 2, 1, go. Okay, can I ask you to change a pipe? Yeah. Yeah, then, yeah. No, you shift, like, yeah, then, yeah, exactly. Yeah. So, okay, so ready? So your 1 minute countdown starts now. Okay, 15 seconds left. Hold on. Okay, good. So 3, 2, 1, go. Okay, can I ask you to shift? Yep. Okay. Your 1 minute countdown starts now. Okay. Ready? So 3, 2, 1, go. Okay, thank you. Can I invite the second year team to come down? Get ready, please. So again, you do the shift. So just like, yeah, yeah. Yeah, sorry, get ready. Yeah. Okay. Are you ready? Yeah? Okay. Okay. So your 1 minute countdown starts now. Yeah, 20 seconds. All done? Okay, so 3, 2, 1, go. Okay, so can I ask you to swap stripes? Yeah, just shift it to the right. Yeah? Yeah, you to the middle. Yeah. Yeah, it's a second line, yeah? The blue one. Yeah, yeah, yeah. Yeah. Yeah, your 1 minute countdown starts now. Thirty seconds left. Ready? Okay. So 3, 2, 1, go. Okay, swap pipe again.
No, that was okay. I think what I understood, if I'm not wrong, is that they decided to use only the ultrasonic sensor and not implement the logic for the color sensor.
Yeah, just yeah. Okay, yeah. Okay. Good. So your 1 minute countdown starts now. Yeah, the top one. Already? Okay. So 3, 2, 1, go.
Did Brunel stop on a target in the final?
In a second, no.
So
The third attempt is stop quick, but missed the target.
you missed the target and the top.
Okay, can we give a round of applause to all the teams, please? Thank you. So now what we'll do is we'll have your presentation, design review, peer review, everything together to decide who will be the winner for the first and for the second year. Yeah, so bear with us. Thank you.
Wait, my backpack. Check in my backpack. What? Electrical stuff. Wait, we didn't brought. Did we brought? Brought what? The batteries. The lithium? No, we brought the 6 volt, not the rest of it. We didn't know 6 volt. The lower one. Was that check stuff? We don't have connections. Hello? We don't have connections. Yeah, no. Behind me. I'm gonna try again.
Is that what the chain's about? So you can pull it down?
Probably.
I didn't even think of that. Have you 3D printed the whole thing? We weren't allowed to do that last year. They wouldn't let us. We were 3D printing because they wanted us to use like the mechanical side of it and actually learn the tools.
Did you get to actually race it then last year? Did you race it last year? Oh yeah,
Yeah, we were the ones that won it. We got the same, well, similar team for my rover, so hopefully that will.
I just need to get one of the actual.
Where did you print it? Oh, the bouncy one. Is that TPU?
Yeah.
How come you took them all off? Are they different to what you raced it? Are they different to what you raced it? Okay, go in. The battery just died. Did you change the battery?
If you reach the top, it will go down really fast. Wait, second thing, who is back down?
The batteries are dying. I think they want to take a picture. Oh. Hi. No, I'm just here to help doing the. Oh, I did it last year. You did, yeah. So you did the line
I don't like button pictures.
Be behind the screen. I have a question to ask you. I'll show you the picture.
Sorry?
In the picture.
No, I don't like pictures.
So this is the arm I'm thinking of going
Yeah.
with. With the motors, could I have them at the bottom or would they have to be in the arm to make it move? Could I have like pulleys? Yeah, like
You
here
could do
and here.
pulleys, but
Sean, come on, go.
more
The
diff-
students are asking you to go.
No, they don't want
Don't be
me.
shy. Yeah, they want. Do you
No,
want
no.
Sean?
All go to stand in for me.
Sean participate. That is
You need me.
participate. You participate. Come on.
Yeah, I was like trying to work a way around it. I think this will be quite easy because we could just
Where,
like
where are the motors in this? Is there one there? How's that?
I just like the simple designs.
Yeah.
You try and like it's kind of simple. Almost laser cut or print out.
Well, yeah, you could laser cut them out with the perspex if you quickly do.
It would just be the mechanism of what we
How about Monday we can have a look at robot shop and see, because a servo in there wouldn't be too bad. Alright, the design is set, so and there's one, I guess, turning that. It's a motor with a little gearbox in it, and it will position for you. So you just give it an angle photo, so it makes it really easy.
So we can just need one.
You would need one for that, one for anything that moves.
So we need like 1, 2, 3, 4.
So you need, yeah, one at the bottom, one on there, one on there, and one to move the job. But it could be, if, look up, I'll show you.
So I had a look on the website and they've got like these obviously made up for like £500.
Yeah,
And I heard some that were 50. I think we've
easily-
got to make it, so we're trying to look at the dark. But also I keep talking to Bertie and Willie and they didn't like the idea that the motor was at the bottom of what they were showing them because they said that it would weigh it down. But then I'm like, we're not lifting like 200 results, so I think it'll be okay.
What sort of weights?
I'm not too sure. I just know it's not. I want to throw these bristles at to get an idea of how it works.
So these are servos.
Okay.
They can be easily embedded into the They're not that heavy, but well, the armor's got 65 kilograms of pull. That's quite strong, but cut these bits out of acrylic, so all you need is service. We just need to find the right one. We could easily. If we find a servo that's useful, that looks like a servo. Yeah, the servo's great for that unit, and then in your R unit, what you just say. So, but you would need to do a little bit of math. So, say you want it to go forward and you want it to be there, you might have to do it. It depends how you do it, but you don't. If you want your, what you can do is you can write some code that will do some reverse kinematics. So, if you want your arm to be there, you can say, right, what angle then you want to do it? Just send it to command. Yeah, there would be a motor up there, turn there. There'll be motor feet there. There must be a robot arm with a Mars rover. And yeah. We've got one. I've seen it in the head, didn't you? But we can do the buttons that we do. I'll have a look Monday. See what service. Yeah, we could do. Not the Ponzo one. Oh, there's three? Oh, okay.
Do we have like a long piece of wire?
Okay. I'll have a look, yeah, I'll have a look Monday. There's one that's black with loads of silver. Silver, okay. I don't know, I'll need to find that. It might be an old one that's coming. Or it might be upstairs coming. Okay. Ideally, you want servos with axles at both ends so that you connect them to a U-shaped bracket. We can have a search on Monday and see what. Once you've got the servos, it'll be quite easy to build up. And if it turns out too heavy, she's worried that it might be too heavy with the servos. The servos aren't that heavy though. Because most of the ones that we've seen commercially have got servos up at the wrist of the joint company. So, and if you try and do pulleys, it's going to be messy.
Do you know where the change is?
It's not that complex, no. Yeah, I don't think we're allowed to use that for a competition. So they need to make their own controller. But if it's a servo, you can easily control it.
We have a chance of a string instead of a chain. We want to see whether the chain, if we don't
You don't have to wait the chain.
Yeah.
You could get a pipe that you could put a hook on. Potentially, if you've got a little bit of string. What have we got in the way of string?
hello, hello, hello. Sorry for keep you waiting. Could you all take a seat? And yeah, we have decided the results. So how? So where can I find?
This is year 2 poster UCLA. Winner of the poster competition, year 2 UCLA.
Okay. Yeah. Hello. Hi. Can I have your attention, please? So we're going to announce the second year results first, and when I call you, please come here so we can have a picture together. So I'm pleased to announce the winning team of the poster competition for the Year 2 Design Challenge is UCL Team A. So, picture? Yeah. Thank you. Sorry, so okay. So the winning team for the presentation competition for the second year design challenge is Brunel. Please come forward. And then, so we don't do the peer review, right? So then overall. Oh, design competition. Isn't that design competition the actual challenge? Oh, the design review. Oh. Okay. Yeah, so the winning team of the design review is Brunel University. And you want to do the first, the overall winner for the. So the second place of the overall design challenge. Oh, sorry, the picture. Yeah. So the second place of overall design challenge for the second year is Brunel University. You want to take another picture? So many. Yeah. That's the UCL for the first. So it's the overall winner.
So for the second year, the overall winner is UCL.
The first years,
All of them?
Yeah. No, this is because of the,
Building up.
Yeah,
Then I'll hand over.
Peer review Middlesex.
Okay. Well done to all the second year teams there. The accuracy that UCL achieved there in the final that we all witnessed, the repeatability, the time, exceptional. So very well deserved on winning that. We now move to year one, and we have another number of awards to give out. We'll start with the peer review. So thank you for everybody's input into that peer review. I hope you found it interesting reviewing other people's designs. When we collated all the results, the winner for that was Middlesex. So Middlesex, congratulations. If you'd like to come forward, come on down. How many they expected in a team? There's loads of thank you. You want me to keep going? Or?
So which one are we doing now? Okay. So we reviewed all your output, and we are now talking about the poster. Can we please have UCLA?
Okay, the next one was for presentations, and that's gone to Kingston University. So if you'd like to come down and get your certificate, thank you.
So the winner of the design competition, the design review competition, is Hertfordshire Team 1. Spare ones.
Yeah, just put them. Third place UCLA.
Okay, that's the overall, right?
Yeah.
Yeah. The overall winner, third place, for the first year design challenge is UCLA. So the second place overall winner of the first year design challenge is Hertfordshire Team 2.
So the overall winner, first year, Middlesex.
The podium ceremony is not quite over because we've forgotten the trophies. So but I'm assuming that they're for the two winners. So if we could have the two winners down, please. So if we could have Middlesex and also UCL. Let's get some trophies. We only do it for silverware, so well done. Let's get some more photos. There's one more. Go on, guys.
Just to let everyone know as well, there is some prize money. So all of the teams that have, so the winners of the overall competition, the presentation, the poster, and the design review, you'll receive some prize money. So I'll be in touch about that.
Close the event. Yeah. So again, thanks very much for coming to Kingston Townhouse to have this first and second year design challenge. And this is the official closure of the event. Feel free to head to the foyer where you had the lunch. There will be some fizzy drinks for you to take if you want. Yeah, thank you very much. Thanks again. Good. Thank you.
Is this the first year that you've done it?
Yeah, it's my first year organized.
The first time that you've used your buzzers. So thank the team, especially.
Amazing.
Yeah. Well, yeah.
It's been amazing. You've done such a great job. Thank you. You had a whole team. Well done. Yes.
Good job.